Hi guys, it's Mrs. Bracy with your video on circle theorems. More things about circles you didn't know you wanted to know until now. Here's how I want you to take notes on this video. You're going to take the worksheet that I gave you in class. There's a copy of it on Google Classroom. If you don't have it with you, you want to print one out. You're going to follow along and draw a diagram in the boxes to the right for each theorem that I talk about, okay? And they're going to be numbered on the video just like they are on your paper. And then when we're all done, you're going to copy the theorems onto 2 flashcards. There's just not enough room on 1 flashcard. I put theorems 1 through 8 on my first flashcard, which is 38, and the rest on the second flashcard. I did put the flashcards on Instagram, and here is what they look like. I just want you to see this right now so that you can see. I did not draw a diagram for every single one on my flashcard because it was going to get really it was just not enough room to do that. But there were a couple that I did because I felt like those ones were necessary to see pictures for. It's up to you. If you want to draw more pictures than I have, that's fine. Otherwise, you can just kind of go with what I did or do your own thing as long as you have them all written down on the 2 flashcards. Okay, so theorem number 1, so work on the worksheet right now, is that all radii or diameters, the slash means one or the other, of a circle are congruent. This is something that probably is common sense, makes sense to you, but here's a picture. Since all of the points on the circle are equidistant from the center, all of the radii are going to be congruent. They're all the same distance from the center. And of course, the diameter is twice the radius. So since the diameter is made up of 2 radii, it works the same for the diameter. Okay, so no matter what, if you have 2 radii, they're congruent. If you have 2 diameters, they're congruent. Seems like common sense, but it is something that we would have to mention in a proof if we're trying to prove something related to congruent parts. Okay, the second theorem is that an angle inscribed in a semicircle is a right angle. Okay, so here's a diagram. An inscribed angle would be ABC, and if you take a look at the arc that ABC intercepts, the arc that goes from A to C underneath, and I'm going to show you, you're going to remember that an inscribed angle is equal to half the intercepted arc, and I'm going to show you that intercepted arc here. So the intercepted arc is a semicircle, and so it's 180 degrees. And so the angle that's inscribed in it, ABC, would be half of that because it's an inscribed angle, so that would be 90 degrees. Very important theorem because, as you know, a 90-degree angle creates perpendicular lines, and 90-degree angles, right angles, are all congruent, so that's going to be a very helpful theorem. Number 3 is that a diameter creates 2 semicircles. I think you already know this one, but when you draw a diameter through the center, you have 2 semicircles, and so I got my nice purple circle here, and then the top half, which is now purple, is one semicircle, and the bottom half, which is now blue, is the other semicircle. Number 4 is that either a diameter or a radius, either one, that is perpendicular to a chord bisects the chord and its arcs. So here's a diagram for you. If I know that the diameter xy is perpendicular to the chord LM, then the chord is bisected. So LZ and ZM would be congruent since Z would be the midpoint. And remember that a bisector goes through the midpoint. The midpoint creates the 2 congruent segments. And then each of the arcs created by the diameter are also bisected. So if you look at diameter xy, we create it's the arc created by the chord. So if you look at the chord LM, the arc is LXM, that's bisected, and that's marked on there for you. And also LYM is bisected, so LY would be congruent to YM if you needed that information. Next is that a diameter or a radius is perpendicular to a tangent at the point of tangency. So I have a radius at OT, a tangent of ST, and I know that those have to be perpendicular. Now if you think about it, I can make a diameter which creates a semicircle, which is 180 degrees, and that semicircle is the intercepted arc for angle STO. And so its vertex is on the circle. It would be half of the intercepted arc. And if I take the arc away, you can see that makes the angle 90 degrees. Next is that tangents drawn from the same external point are congruent. Pretty straightforward. If you have two tangents and they share a point outside the circle, then those tangents have to be congruent to each other. So HJ has to be congruent to HF. I like to call this the ice cream cone theorem because if I turn it that way, it reminds me of an ice cream cone. And so the two sides of the cone should be congruent. Sometimes I flip it upside down and call it the happy ending sundae like you get at Friendly's. But either way, you end up with two tangents that are congruent, and that's helpful to know. Okay, so here's a try it. I want you to try to find the value of x on this diagram. And I'm going to just be quiet for a second so that you can copy it down or do it real quick in your head maybe, and then a question will pop up on the screen so that you can answer it. Okay, so next is number 7, parallel chords intercept congruent arcs. So if I know that chord CD is parallel to chord AB, then arc AC is congruent to arc BD. Notice that that does not necessarily tell us anything about arc CD and arc AB, so it has to be the arcs that are contained inside the parallel lines that are congruent. That doesn't, again, tell us anything about the outside arcs. They may or may not be, okay? So it's just these two inside arcs right here that we know are congruent since the chords are parallel. Number 8 is that congruent central or inscribed angles intercept congruent arcs. So we'll look at the central angle one first. In this diagram, I'm given two central angles, CAD and BAE are congruent. And so, there we go. That means that arc BE is congruent to arc CD. Now this should make sense because arc BE has the same measure as angle BAE. And arc CD has the same measure as angle CAD. So if the angles are congruent, then the arcs have to be congruent. So we have that conclusion. Arc BE is congruent to arc CD. Okay, this also works with inscribed angles. So my little smiley faces are going to represent congruent arcs. Now, yes, I was also given that these were congruent, okay, but we're going to actually talk about that in a minute. So let's look at these two. So if I know that these two smiley face angles are congruent, then I know that the arcs they intercept are also congruent. So arc CD would be congruent to arc AB. Okay, think about this. An inscribed angle is half the intercepted arc, and this inscribed angle is half the intercepted arc. So if the angles are congruent, that would make the arcs congruent. So we have the conclusion that arc CD is congruent to arc AB. Next is congruent central angles have congruent chords. And so it's very similar, except this time it's the chords that connect the two parts of the arc. So chord BE is congruent to chord CD. So that one is similar to the arcs, just with chords. Number 10 is that congruent chords intercept congruent arcs. So if I know that chord AC is congruent to chord BD, then I know that arc AC is congruent to arc BD. And so arc AC is congruent to arc BD. So congruent chords will create congruent arcs. Backwards, congruent arcs have congruent chords. So if I begin by knowing that arc LM is congruent to arc XY, then I can say that chord LM is congruent to chord XY. So chord LM congruent to chord XY. So this is the same as the previous theorem, but backwards. And so it is important how you word it because it depends on what you start by knowing. If you start by knowing that the arcs are congruent, then this is the one you would use. Congruent arcs have congruent chords. Number 12 is that inscribed angles that intercept the same arc are congruent. So we're going to look at two inscribed angles here with our little smiley faces again. ADB and ACB, the C got cut off down at the bottom here. And so notice that they intercept the same arc, arc AB. Okay, so since they intercept the same arc, they have to be congruent to each other because they are both equal to half of its measure. Okay, so if the inscribed angles intercept the same arc, then they are congruent. And there's the arc that they intercept. And there it is again. And here's a question to try based on that theorem. And so I'll give you a minute to figure it out, and then a question will pop up on the screen. Okay, number 13 is that central and inscribed angles that intercept congruent arcs are congruent. So let me get some information up here for you. If arc PQ is congruent to arc LM, then angle LOM would be congruent to angle QOP. Okay, so if the arcs are congruent, then the central angles that intercept them are congruent. That works for inscribed angles as well. Okay, so if an inscribed angles intercept congruent arcs, then they have to be congruent. Number 14 is that congruent chords are equidistant from the center of the circle. So if WX is congruent to YZ, then LC has to be congruent to CM. So if the chords are congruent, they are the same distance from the center. So you can draw in a perpendicular distance from the center to the line and say that those two perpendicular distances from the center to that chord are congruent to each other. They're equidistant. Okay, so try one more. Find the value of X. Okay, the last thing is two other theorems that we have actually used throughout the year a little bit, and so we're just kind of writing them down now. The first is that angles or segments with equal measures are congruent, and this is the one we used when we had to switch back and forth between measures and talking about the segments themselves being congruent. Technically, in a proof, we should be using congruent, so if we know that their measures are equal, we have to say they're congruent before we move on with the proof. So we've used that a few times, and that can still show up here and there if we need it. And last, halves of congruent quantities are congruent. We have used that one a few times. Makes sense. If two things are congruent, then half of each would be congruent as well. And that is not something that is obvious. That is something that you would need to state in a proof if you're using it. Okay, so you can, those you don't have to draw pictures for. You'll just jot them down on your flashcard. Okay, so your last task is to just make flashcards 38 and 39 with these theorems on them. And again, here's what my flashcards look like. You're more than welcome to just copy my flashcards or, copy what you have on the worksheet onto flashcards. Like I said, if you want to draw more diagrams than I have on the flashcard, you're welcome to, and you can certainly set it up differently if you think that would work better for you. But these theorems are going to come in very handy, not only when you're doing algebraic problems, but definitely when we're doing proofs. So you're going to want them written down so you can bring them to class with you. Okay, I hope this was helpful, and I will see you in class.